So now we bring ourselves to our second nucleophilic substitution reaction. This is known as SN1. SN1 has some similarities to SN2 in that the S still stands for substitution. The N again stands for nucleophilic. But the 1 here tells us something different is going on, because that points to now a unimolecular rate determining step. And so just based on that information alone, we know that the mechanism, the reaction itself, is going to have to be different from SN2. How do we know that? Well, with SN2, everything was happening in one step. That meant the only step, which was the rate determining step, involved both the nucleophile and the electrophile. But in an SN1 reaction, if the rate determining step is unimolecular, then that can't be the case anymore. Now, a second interesting thing to note before we get into the SN1 is here's an example. So we can see again that a nucleophile here, I-, is replacing some sort of leaving group. But we know this can't be an SN2 reaction. It has to be something else. How do we know that? Well, we've said that tertiary leaving groups rarely undergo SN2 reactions. So how does this reaction work? What is the mechanism for an SN1 reaction? And how is it that a compound like this, a tertiary alkyl halide, which is terrible for SN2, turns out can work well for SN1? Well, we could think about some of the things that having more substituents would help. And what are some of those things? When do we get a benefit from having more substituents? Well, one of the most common things where more substituents are better are for carbocation stability. The more carbon groups you have, the more stable your carbocation is. And so in an SN1 reaction, what happens is that in the first step, the leaving group leaves. And as a result, we get a carbocation. Then, in a second step, the nucleophile attacks. So the net result for an SN1 reaction looks very, very similar to what happens in an SN2 reaction. But the mechanism is very different. Now, which step here is the rate determining step, and how does that help to explain the fact that this reaction is unimolecular? Well, logically, which of these two steps do we think would be slow and which do we think would be fast? So this first step, which is formation of an unstable cation, is generally going to be slow. We need to add energy in order for that to take place because we're going from a stable compound, an alkyl halide, to an unstable carbocation. In many cases, when you do something like this, this is not something that's necessarily going to be easy to do. And so we will see that from almost all SN1 reactions, this is our rate determining step. This should also make sense because our second step quenches an unstable cation. And so we would expect a step like that would occur fairly readily, doesn't require a huge activation energy, and is generally going to be fast. So for an SN1 reaction, typically the rate looks like rate is equal to K times the alkyl halide. And so we can see that it is unimolecular. The rate is only dependent on the concentration of the alkyl halide. The rate is not dependent on the nucleophile. But that's our basic SN1 reaction. Leaving group leaves in the first step, forms a carbocation, and then the carbocation gets attacked by a nucleophile to form the product. Alright, now what are the things that affect an SN1 reaction? We can look at the same factors that influenced SN2 reactions. So we're talking about sterics, solvent, leaving group, and nucleophile. Some will be different, some will be the same. But we're going to start with the sterics, or the degree of substitution. Because in an SN1 reaction, this is actually opposite of SN2. Why is that? Well, if we think about what we've learned previously about carbocation stability, what is the most stable carbocation? Typically tertiary. And tertiary is more stable than secondary. And secondary is typically about the same as our allylic or benzylic cations, which are more stable than primary, more stable than methyl. If you've forgotten what these terms mean, allylic means that the carbocation is adjacent to an alkene, and benzylic means that the carbocation is adjacent to an aromatic ring. And in both cases, both the allylic and benzylic cation are resonance stabilized. So why does this matter? Well, recall that we've said any factor that stabilizes an intermediate also stabilizes the transition state. Well, if we stabilize the transition state, this lowers the activation energy. So what's happening with the degree of substitution is as we increase substitution, the carbocation intermediate becomes more stable. We increase the substitution, the intermediate becomes more stable, If the intermediate is more stable, then the transition state is more stable, and we lower the activation energy. Now, what about the sterics? So we can see now that increasing the substitution definitely helps in an SN1 reaction. But what about the sterics? Because for an SN2 reaction, more substitution meant that the electrophile was blocked from the nucleophile attacking. Well, a carbocation, we could draw it a couple different ways. But a carbocation is sp2. What that means is that the carbocation is going to be trigonal planar. And so our three substituents, which even if they were just as simple as methyl groups, are all contained in one plane. That empty p orbital is above and below the plane where the substituents are. So if a nucleophile is going to attack, where does it come from? Well, it's going to come either from up here or from down here. But the key is the three substituents on that carbocation are all in the same plane. And so the substituents don't block nucleophilic attack. So we can sort of summarize this as saying that for an SN1 reaction, more substitution increases the stability of the carbocation, which increases the rate of the reaction. In addition, because the carbocation is planar, the substituents don't interfere with the nucleophile attacking. Now, this also leads to one other detail. If we look at that carbocation, and again, here's our p orbital, which side will the nucleophile come in from? Will it come from the top or the bottom? Well, because the cation is planar, the nucleophile can attack from either side. And so if you end up in a situation where it's equally likely to come in from the top to the bottom, it leads to racemization. So this is another big difference between the SN1 and SN2. With the SN2, the nucleophile came in from opposite where the leaving group was. Because it came in from opposite the leaving group, we got inversion of stereochemistry. In an SN1 reaction, though, it can attack from either side. And so it will not be inversion, but there can be some inversion, and there can be some retention of stereochemistry. What determines that? Well, that gets a little bit beyond the scope of this course, but basically it depends on how strongly associated the cation and leaving groups still are. If they're strongly associated, that leads us on one path, and if they're completely dissociated, that takes us completely to racemization. But what we need to know here is sort of what I've put at the bottom. In an SN1 reaction, it generally tends toward racemization. And remember, racemic means that we have 50% R and 50% S.